Chapter 8, another chapter that's really important. It's going to come up a lot in your own research if you use econometrics. This is the chapter on multicollinearity. And this problem occurs when, oh, sorry, I didn't erase this from the last chapter. This problem occurs when two variables move together or move in the exact opposite direction, but when they're correlated. Because it makes it difficult for the computer to tell which one is really causing the changes in the dependent variable. For example, I gave you something earlier where I said, okay, let's say that we've got grade sub I is beta sub 0 plus beta sub 1, hour sub I plus beta sub 2, SAT score. Sorry, I always run out of room for that. Okay, so let's say that that is the true equation. Oh, I forgot my sub I. Let's say that's the true equation. And of course, you want to include hours and SAT if that's the true equation, because if you leave one out, you've got omitted variable bias. And those are measuring two different things. One is measuring how many hours you studied for this exam in, say, fall semester 2020, and one of them is what was your SAT score that you used to get into TCU. And so the idea is that this was your immediate preparation for the exam, and this is how well prepared you were back in high school. It is a proxy, it is an approximation. You're going to have to use a lot of proxies in economics where we couldn't get exactly the right variable, but we're hoping that this one is approximately the same. So this is a proxy for your high school preparation. And those are two different concepts. But the problem is that they're likely to move together. That people who have higher SAT scores are likely to study more, and people who have lower SAT scores are likely to go to Texas Tech. That's just a little joke there. Are likely to not study as much. All right. I'm not sure that the University of Tennessee, my alma mater, would compare favorably with Texas Tech, but anyway. Now, why is that a problem? Because the computer is going to do this. It's going to say, wow, I know there's something significant over here. I can tell that when these numbers go up, this goes up. And when these numbers go down, this goes down. But boy, am I having a tough time telling the unique contribution of this versus this because they move in the same direction. I don't know, I usually end up using a sports example of some sort here. Let's say that your team tends to win when you have fewer interceptions and when you have more rushing yards. Well, the thing is, you're going to have those at the same time. So if you build a lead in the first half, then you are going to tend to run the ball from then on, because if you are familiar with the game of football, you are taking fewer risks by running the ball. You also aren't going to make a lot of gain in terms of yards. But if you're ahead, you don't need that. All right? All you're trying to do is to hold the ball longer than the other team. So you're going to get more rushing yards and you're going to get fewer interceptions because you're not throwing the ball as much. So which one caused you to win? It's hard to tell the difference, right? And that's exactly the problem here. That what's going to happen is the consequences are the estimates, if there's severe multicollinearity between these two. There's always some multicollinearity. There's nothing you can do about it. There's always some correlation, even between two sets of totally random numbers. You're going to tend to have some correlation just by chance. But if there's a very high level of correlation, and we'll talk about what high means a little bit later in the chapter, then what's going to happen is the estimates are unbiased, so that's good. The estimates remain unbiased. On average, as you take samples of this from the entire pool of all students who have ever taken intro micro, you're going to tend to, your estimates, your beta hats will tend to cluster around the true betas still, if you remember this from a previous chapter. So it stays unbiased, but your t-scores are going to fall. Because, well, the technical answer is that the variances increase and the standard errors increase, but the simple intuitive way to think about it is the computer's just less sure now. The computer's like, man, I know something's going on here, but I can't tell this one from this one, so I'm going to give you a low t-score to indicate to you that I don't have a lot of confidence. The adjusted R-square, however, is largely unaffected, all right? So the overall fit and the estimation of the coefficients are largely unaffected. But when you get a regression that has a high adjusted R-square, what's high? That's something I should bring up right here. What's high? It depends on the literature. In some literature, they expect you to have around 0.9. It depends on what other people got. I showed you what I had here, 0.17. Actually, that's pretty good for a study of what I was looking at. But if you have a relatively high adjusted R-square and hardly anything significant, you're like, well, wait a minute. How can I have explained a great deal of what's going on, but none of these variables is significant? That's a very common sign of multicollinearity. The computer knew there was something going on here, but because it couldn't differentiate between these two, it's required to give an estimate of the confidence on this variable, on this coefficient and this coefficient, and it's going to give you low t-scores. All right, so that's the consequence of multicollinearity. Let me back up a little bit and talk about perfect versus imperfect. I got a lot more to say about that, but let me back up for just a second and do perfect versus imperfect. Perfect is when you've basically included the same variable twice. All right. What if you had beta sub 1 hours, beta sub 2 minutes? I also measured how long students studied in minutes. Okay, well that's the same frickin' observation as this one over here. And because it is a direct linear relationship, because one variable can be completely explained by the other, as was explained in, I believe, chapter 4, the computer won't even estimate it. It said, I can't do this. What the hell? What you trying to do to me? I can't do this. You have tried to make me explain this phenomenon with those are the same variable. How do you expect me to figure out the unique contribution of this relative to this when it's really the same variable? So it won't even run it. It will say you have perfect multicollinearity and it will spit it back out at you and you will feel ashamed. That's very rare. And almost 99.99999% of the time it's going to be because you did something dumb, like this right here. They're like, oh crap, that's right, that's the same thing. Obviously, probably not as clearly obvious as this, but something where you've just included the same thing twice. All right, so that really, okay, how do you solve that kind of multicollinearity? You drop the one that you don't want to have in there. You drop the minutes or drop the hours, either one, doesn't make any difference, the same variable, just drop one. Imperfect is a pain in the neck because, as I said, you're almost always going to have it. And, well, your choices of what to do about it. Do I want to do that next? No, this is just going through the explanations. Overall fit, yeah, I told you that. Just R-square won't fall much, if at all. Okay, detection. I guess let's talk about detection first before I do what to do about it. Well, I already mentioned one thing. If you have a regression with and that's something I like to put on an exam. I'll give you one with a high adjusted R-square, but a bunch of insignificant t-scores. Hey, what do you think's going on here? Oh, I'll bet there's severe multicollinearity. There's no commonly accepted test for multicollinearity. There's one in the book called Variance Inflation Factors. I don't know that it's all that popular. I've used it. I don't think I've ever reported the result with it. Really and truly, and maybe I should just jump to this, usually you don't do anything about this because you can't. Because you can't do anything about it. Let's say you ran this regression, this one in blue here, and you had a problem of severe multicollinearity. Can you drop one of those two variables? Not really. They both make sense theoretically. It makes sense to include how well they were prepared from high school. It makes sense to include how many hours they studied. So unlike the example of hours and minutes, it doesn't make sense to drop one of them. So you're screwed. This is one of the things that you really hate to see when you're doing empirical research, is to find out, crap, two of these variables, each of which I believe makes perfect sense theoretically and must be included, they're highly multicollinear. And so they are causing the t-scores to show that they're insignificant, even though I got a pretty decent adjusted R-square. And there's just nothing you can do about it, because if you can't justify dropping one, well, let's think about this. What if you drop this one? You just bias the estimate of beta sub 1. What if you drop this one? You just bias the estimate of beta sub 2. At least with multicollinearity, there's no bias. There's just less confidence. The pool from which you draw possible beta hats has become wider. There's a little, I don't know if I want to go over this in great detail or not, but here is his, which one is this? I haven't said which table it is, sorry. It's in that chapter 8 there. But when you have severe multicollinearity, what happens is it becomes much less confident about the beta hats it's estimating. The average beta hat is still centering on the true beta. Notice that for both of them. The average one is still centering on the true beta, but you get a lot more variation. The computer with multicollinearity is kind of saying, I don't know, geez, maybe it's this. All right, so I'm having a tough time telling between these two. 5, you know, and so on average, its guesses are still centered around the true number, but it's having a much wider variation, whereas when there isn't any multicollinearity, I think that's a 5. I'm pretty sure that's a 5. I'm pretty sure that when this goes up by 1, that goes up by 5. When there is severe multicollinearity, it's like 5, 6, 3, I don't know. Like, give me a break. So that's what happens with multicollinearity. Now, as I say, you often don't do something about it. One of the things, when you do have that situation though, when you do end up with, let's say it's a big regression with more than just these two. If it's just these two and you get a pretty high adjusted R-square and they're both insignificant, you're like, oh, there's got to be a multicollinearity. But if it's a big regression with a lot more variables and some of them are significant, you're not going to be able to tell whether the low t-scores here are from multicollinearity or they're just not very significant, all right? And so in that case, you might want to do a partial correlation coefficient. And I've got the command here in Stata. The command is, if I can spell correlate correctly. John. Correlate, and I'll use our example here. Correlate hours in SAT. Tell me what the correlation is. Correlate hours in SAT, and then it will spit out a little matrix here. Let me show you. First of all, the corners will be 1. Guess what? Hours is perfectly correlated with hours, and SAT is perfectly correlated with SAT. What you're wanting to see is this number right here. Like maybe it's 0.9. Then you're like, oh crap. They're 90% moving together, all right? Or it's 0.7, or it's 0.2. You're like, yes. They're not correlated. But if it's 0.2 and they weren't significant in this big regression, that doesn't lead you to change the regression, because remember, theory is always number 1, but it does give you a lot less confidence about their significance. When they're not getting the low t-score because they're correlated. It's for another reason. Whereas when you get this, and it's definitely something you would report in the paper you were writing, when you get this down here, you're like, well, neither of them was significant. However, they were also highly correlated. So I suspect I had a serious problem with multicollinearity. How do you fix it? You can't. There's nothing you can do. This is a very depressing chapter because it is a very common problem and it's very difficult to do anything about it. There are some things you can do. I'll give you an example here in a minute. Okay, here's his 3. This is a fast chapter here for given that it's an issue that comes up. Well, there's not a lot to say about it, unfortunately. Remedy 1, here's his 3 remedies. Remedy 1, do nothing. The existence of multicollinearity might not mean anything. If your coefficients are still significant, then you're done. Furthermore, if you delete a multicollinear variable, I'm just summarizing what I've already said, that belongs in there, now you've created specification bias. So, you know, every regression we run, we risk encountering a specification that accidentally works on our specific example. So you got to keep the theoretical stuff in there right. Remedy 2, drop a redundant variable. Okay, check this out. What if you included SAT score and ACT score, both? Those are not the same in the sense that hours and minutes are, but you don't need both of them, all right? Those are both meant to pick up on how well prepared the student was for college, but you don't need SAT and ACT, so drop the redundant variable is what he is suggesting in part 2. Two or more variables in an equation measuring essentially the same thing might be called redundant. Dropping a redundant variable is nothing more than making up for a specification error. In fact, you should never have had both of them in there. It never made sense. And in a case of severe multicollinearity, doesn't really make the difference which one you drop, whether you drop SAT or ACT, but drop one of them. Now, and then his third remedy, which you can't do, but I mean, he's right to include it. Increase the sample size. That the larger the sample size, usually the more it will allow greater variation between these two. But if you could have got a bigger sample size, you would have already done that. Now, something he doesn't mention here that is possible is sometimes you can create a single variable from the two multicollinear variable. And I'm trying to think here, I couldn't really do it with that. But you can create a ratio, for example, of hours to SAT. That's not going to work here. But there are instances where you can make a third variable out of the original two, and you're going to lose a little bit in terms of the explanatory variable, the explanation of this variable versus this one, because now they're combined. But if you weren't really interested in that variable in particular, then it will get rid of the insignificant t-score, and you can look at the other variables. But that may come up now and then that you're able to do that. Chapter 8, that was it.